All right. So good afternoon again. I saw a few more people join. Let me know how you're doing. How is everybody doing today? You can let me know in the chat. Feeling good? Hope you're feeling healthy. There's a lot going on this season. It's flu season. It's been COVID season for a while. Lots of things going on. Being indoors a lot, cloudy, rainy weather, all those things can affect your mood. Instructors are no different. So I'm glad y'all are doing good. It's afternoon. You've had some time to wake up. We're going to do two things today. I feel you on the tired piece. You know that I wear the Dr. Hefner hat while we're in class, but sometimes Baby Hefner makes an appearance. And I also wear the Mama Hefner hat. I'm also Wife Hefner. And Mama Hefner got 4 hours of sleep last night because Baby Hefner decided it was time to play. So, I understand tired. Your instructors are not always 100% with it. They don't always want to be doing what they're doing at that time. But I like y'all, and I'm here. So, we've got two things to do. Exam 2 review, which I have a few questions that are really reaching back to Chapter 3. We're going to do some review of Chapter 4 material as we cover Chapter 5. And that's the second thing we're going to do. Cover Chapter 5, which is the periodic table. As you know, you have an exam coming up. It will be live tomorrow morning, and it'll be available through the end of Friday, 11:59 p.m. Eastern Time. It's multiple choice. It's about 30 questions. No partial credit this time because there's really no math. So take your time with the exam, read it through, answer the question. Don't just choose an answer, but answer the actual question. And there's an exam 2 review packet already posted along with the answer key. So we're going to do a few of those questions now, and then we'll jump into Chapter 5. Before we do, if you have questions about the exam, this is a good time to ask them. Otherwise, I'll ask again at the end of class, and if you think of something, you can let me know then too. If you have a question, ask it. Otherwise, let me know if you're ready to move on. Okay, so I see one question. I'll answer that, and then we will move on. So the question is, can you use your notes on the exam? The answer is no. But for the exam, you get a periodic table. And for Chapter 4, and what we're going to do for Chapter 5, I recommend that you practice drawing your cheat sheet. So you can recreate that cheat sheet. Just start the exam in Respondus, and then draw out whatever you need to draw out. You can have all the markers, color pencils, whatever you want. Scratch paper for your exam. Remake your cheat sheet in that exam setting. Just start the exam. And then you can use that to take your exam. Don't bring it with you, but if you can recreate it, that's totally fine. That's completely fair. All right, let's get started. First exam review question. How many neutrons are in the nucleus of an atom of cobalt-60? If you don't have a periodic table, you need to pull one up. You can use the one that's already on Blackboard. I'll give you 1 minute. You can put your answer in the chat. A, B, C, D, E. How many neutrons are in the nucleus of an atom of cobalt-60? All right, so it's been about a minute. I know there's still some folks logging in. Welcome back. We've got to figure out how many neutrons are in the nucleus of an atom of cobalt-60. What does this 60 mean? 60 what?60 is the mass number. And that's equal to the number of protons plus the number of neutrons. For cobalt and any other element, you can look at the periodic table and find the atomic number. For cobalt, that is 27. And we're already told what the mass number is. You subtract 27 from both sides. And you get B. Let me know if you got questions or if you're ready to move on. Then let's go. Which of the following properties of gasoline is a chemical property? I'll give you a minute to read it, and you could put your answer in the chat. So everyone who's chimed in has said E, none of the above. I agree. If you had to classify these, colorless liquid, density, boiling point, what are they? It's not a chemical property. Is it a chemical change, or a physical property? Yeah, these are physical properties. Let's move on to the next one. This one does have a little bit of math. It's one of those weighted average questions. I'll give you 3 minutes to do this, and then I'll check back in and we can go over it. If you didn't get to an answer yet, that's fine. You can keep working. I'll start setting up the problem. We've got element X with 2 natural isotopes. We've got X63 and its atomic mass. We also know the percent abundance of X63. We've got X65 as well, and that's its atomic mass. I like to make a table. Won't always be easy with just 2 isotopes. Let's fill in the table. For X63, we know its atomic mass, and we know the percent abundance. For X65, all we know is the atomic mass. We seem to be missing the percent abundance. The key to this problem is remembering that for percent abundance, it's always going to total 100%. So the percent abundance of X63 plus the percent abundance of X65 is always going to equal 100%. You take that 100%, you subtract 69.17%, and that will give you 30.83%. I'll highlight all of the given information in the table so that it stands out what we had to figure out. To convert the percent abundance to something a little more usable, I like to write it as a decimal. You divide by 100 to get the decimal. And now we can put together our equation. This is the equation that you put together. And when you do all that and take into account sig figs, you get 63.55 AMU. Remember that we have the contribution from the X63 and the X65. How do we feel about that one? Good. You'll definitely see something like that on the exam. So if it's not good for you, make sure that it becomes good. You already missed office hours today, but if you need to set up time, let me know right after class or send me a private chat during class so you can get in there and get some help before the exam. I threw in a couple more questions. These are from chapter 3. So take a second. I'll give you about 2 to 3 minutes to read through these and answer them. And then I'll answer them. I'll make sure everybody's kind of ready to go over them, and then I'll answer them. We'll get started. This first question, you might be looking at it like, when did we do that? It's from chapter 3. At the end. It's a conservation of mass question. We talked about the law of conservation of mass, saying that mass is neither created nor destroyed. So when you do a chemical reaction, the mass of the reactants is equal to the mass of your products. For this problem, the reactants, well, there's actually only one. It's limestone. And the mass of the limestone is equal to the mass of the calcium oxide plus the mass of the carbon dioxide. Those two are given. When you add those two up, you get 10.11 grams. So I threw that one out there just because it's part of chapter 3. It's just one of those obscure things that you might not remember. How does everybody feel about that one? If you didn't get it or you looked at it like, what? Hopefully that kind of jogged your memory. And if not, hopefully it makes sense. For the second one, we have to figure out how many carbon atoms there are in vegetable oil. Let's identify all of the carbon atoms. We've got some there, here, and this little sneaky one here. When we figure this out, we're going to take the 3 carbons that are out here, plus we've got all the carbons in parentheses. There's 17 plus 1. Then we have to multiply that by the number on the outside of the parentheses. So what that really is 3 plus 18 times 3. And by 3, I mean, yes, that is correct. At first I was like, wait a minute, what? No, I wrote it right, I think. So the 18 comes from, we've got 17 carbons here, C17, H33, but then we have another carbon here that doesn't have a subscript. So the total number of carbons within these parentheses is 17 plus 18, or 17 plus 1 for 18. When you do that math, 18 times 3 is 54. You add another 3 on, and that's 57 carbon atoms. Make sure that you get all of whatever atom is asked about, because it's very easy to miss one. And the exam is multiple choice. So there won't be any partial credit for saying, oh, I left one out. Then that's the wrong answer. I can't really help you out there. We good on this one? So that's the exam review for now. Like I said at the beginning of class, if you missed it, we're going to be doing Chapter 4 review while we cover Chapter 5. I'm not going to review kind of the history lesson. That you'll need to review on your own. But when it comes to writing the electron configurations and making sure you understand the sublevels and the order, that kind of thing, we're going to go over that. And then we'll add to it. So just hold on for that. I want to make sure I catch everybody. So I'll repeat myself. Sorry if you're already here. But mastering chemistry, I know there was a problem over the weekend. You have an extension. Chapter 3 and Chapter 4 are due at the end of Wednesday, March 3rd. That's 11:59 p.m. Eastern Time, March 3rd, tomorrow. You still have Chapter 5 to do, which will be due on Sunday, on top of your exam. So don't get behind. Try to work on Chapter 5. Some of those questions may help you study for Chapter 4, which is part of the exam. So make sure that you take note of that. There's also some other announcements just to kind of keep you on track with dates and things at the end of the lecture. With that said, we're going to jump into chapter 5. There's a little bit more history at the beginning of chapter 5. I'm not going to go over all that in the live lecture. You can read it in the textbook, you can look at the notes, watch the YouTube video that's already posted. It essentially goes over the history of the development of the periodic table. So we go through a few names, talk about a few things, and then we get to the periodic table as we know it today. That's where we're starting. This slide of the periodic table summarizes several things that you'll need to know about the organization of the periodic table. I'm not going to walk through every single one of them. I'm just going to point out a few, but make sure that you watch the video to know what it is you're responsible for. So that's what we're doing on this slide, giving you an idea of the kind of material you will need to know for your next exam, exam 3, which covers chapter 5 and chapter 6. So you'll need to know how the periodic table is arranged, which is according to increasing atomic number. There are groups and periods. Groups are the vertical columns. Periods are the rows. Some of the groups have common family names, which a group is also sometimes called a family. The common names that are listed on this periodic table that I talk about in the video, you will need to know. You'll need to know where the transition elements are, the representative elements, lanthanides, actinides. There may be a couple of other little details here and there. The video will be really helpful for that. So I'm just giving you an overview of what you need to know. So does everybody have an idea of the types of things they'll need to know about the periodic table? Great, because I'm leaning on y'all to look at that so we have more time to work on practice problems for the tougher concepts in this chapter. If you have a periodic table, this is a good time to pull it out and start drawing on it if you have one to draw on. We're going to cover 3 different periodic trends that you can draw on that periodic table. And this is part of what I would recommend for your cheat sheet that you kind of practice making and then recreate. Obviously, chapter 5 is not going to be on this coming exam, but it will be on exam 3. So make that kind of a habit to make your own cheat sheet and kind of memorize how to do it if that helps you, so you can recreate it in the exam setting and then go from there. The first trend we're going to cover is atomic radius, and that just speaks to the size of the atom. Atomic radius decreases as you go up a group, so from the bottom to the top, and from the left to the right of a period. So as you go across the periodic table from left to right, atomic radius decreases. So if you have color pencils and markers or whatever, I would say to put your arrows for up and over and write atomic radius decreases here and here, like that. Let's talk a little bit about why it decreases. We said that with the periodic table, we've got periods, right? These are the rows. Those rows correspond to the different energy levels. And in chapter 4, we said the bigger the N, which is the principal energy level, the farther away the electrons are from the nucleus. So if you are in N equals 5, your electrons can be pretty far away. If you're in N equals 1, you don't have enough energy. Those electrons are not going to be as far away. So that's why the atomic radius, as you go from the bottom of a group to the top of a group, it gets smaller. When you go across a period, though, we're talking about something else. So let's say we're looking at boron all the way through fluorine. This is actually N equals 2 over here. We have N equals 2, the same principal energy level, but we keep adding electrons. It's the principal energy level, the main energy level. It tells you what row you're in on the periodic table. So it's like it's a quantum number, but it's related to the energy of the electrons that are a part of the atom. Let me know if that rings a bell. Okay, no problem. You're adding electrons to the same principal energy level, and you're increasing the number of protons in the nucleus. You're not expanding the size of your energy level. So those electrons and protons, you're increasing those, they have more attraction to one another. And that attraction causes the size of the atom to shrink. You don't need to know this in like super detail. There may be a question on it about why does the radius decrease in size as you go up a group. Just know that it's related to the energy levels. Lower energy, smaller atom. So this is really kind of more for the, I'm interested in this, or this is a little bit intriguing. I want to know more. That's your little bit more. If you're not interested and you don't really care, that's fine too. Everybody's not going to be a chemist. You can just say, all right, that's cool, Dr. Hefner. We can move on. So if this doesn't 100% make sense to you about the why, don't focus on that too much. Just make sure you know the trend. The second trend is metallic character. And what that really means is we're looking at how easily an element gives up an electron from its outermost energy level. Metallic character has a similar trend to atomic radius. As you go up a group, so from the bottom to the top, and left to right across a period, metallic character decreases. So if you can remember that metallic character and atomic radius are the same trend, as in they decrease in the same direction, then that will help you on exam 3. Questions about the trends: atomic radius, metallic character. I'm going to guess that's a no. If you do have a question, feel free to ask it if we've already moved on. So in addition to the general trends that you can draw for the whole entire periodic table, we can also predict physical properties and chemical properties of elements. The reason we can do this is because elements in the same group have similar properties. They also exhibit trends, overall trends. When it comes to physical properties. This table, if you watch the video or if you look at the textbook, might look a little familiar. It's the same table, but this time we're going to talk about lithium and fill in some of the blanks for lithium based on the trends that we see. Atomic radius, we just talked about that. Cesium, this is near the bottom of the periodic table. Lithium, near the top. We've got the biggest radius down here. And we're going to go all the way up to the smallest. We already know that trend. But if we just had this table and we didn't know that general trend, we could look at the numbers for the atomic radii of all these different elements. And what do you notice? Each time you move up the periodic table, the radius is getting smaller. While we can't necessarily put a number to what the atomic radius of lithium is, we can definitely say that it's less than 186 picometers. Does everybody see that? So if I asked you, I'll give you some options for what the atomic radius of lithium could be. Let's say these are the options. These are our 3 options. Which one do you think makes the most sense in terms of a radius for lithium? Yeah, 130 would make the most sense. 57 is definitely less than 186, but that's a really big jump to go from 186 picometers to 57. We're not seeing big jumps like that. That's the kind of question you'll need to answer on an exam or with your homework. Let's do this again for melting point. Oh yeah, go ahead. It's because it's got to be smaller than the one that comes before it. We're going from the biggest radius to the smallest. Sodium is 186. So the radius for lithium has to be smaller than that. Since sodium is less than 200, lithium's radius should also be less than 200. Okay, good. Let's try another one. Let's look at melting point. What's the trend that you see going from the bottom of the group to the top? Is the melting point increasing or decreasing? Yeah, it's increasing. So, on an exam, if I gave you options for what a potential melting point could be, which one of these would you choose? $128.7 seems about right. So it's got to be greater than 97.8. So that means 59.2 is definitely out of the running. Now we've got two more that are greater. But when you look at the trend, the jumps are not that big. To go from a melting point of 97.8 degrees Celsius all the way to 500 seems really, really big, when all that we've seen is maybe jumps of 10, 20, 30. So that kind of reasoning will come in handy when you're doing the exam and the homework with Chapter 5. Are we ready to do some practice for this? Because I have a practice problem for you. Here's your problem. You have to predict the density of barium, and you are given the densities of calcium and strontium. I've also included the group that includes all three of these elements so that you can figure it out even if you don't have a periodic table. I'll give you 2 minutes to read over the question and put your answer in the chat. Let's go over this one. It seems like everybody that chimed in already has chosen D. And I agree with that. For those of you who may be still working, or you're like, I don't understand that, I'm going to go over it. Let's place these numbers on the periodic table. We've got to figure out barium. We know the density of calcium is 1.54 grams per centimeter cubed, and strontium is 2.63 grams per centimeter cubed. In a test-taking environment, the best thing you can do is eliminate answers that you know are not correct. Since it seems that the trend is an increase in density as you go from the top down to the bottom, the density of barium has to be bigger than 2.63. So you can automatically get rid of the first 3 answer choices. Now you're down to a 50-50 shot. Much better odds. The difference between 1.54 and 2.63, that's roughly 1 gram per centimeter cubed. It's a little bit more than that. So the jump between strontium and barium, the difference between those two should also be approximately 1. The only one that fits the bill for that is 3.72. So you could do the math to figure out the exact difference between these two densities and then figure it out that way and you'll get the same answer. But you can use your kind of mental math and reasoning and you don't even have to touch your calculator. So does everybody understand how we got 3.72 instead of the 4.17? Good. There's going to be a lot of reasoning. So chapters 3, 4, and 5, lots of reasoning, not really much on the math. Let's keep going. We talked about physical properties. Now let's talk about chemical properties. If you watched the video, then you might remember Mendeleev. He is considered the father of the modern periodic table. The reason is because he took all of the known elements and arranged them based on the formula of their oxides. So when you have a compound with an oxygen, it's called an oxide. And he said, let's arrange all of these elements based on how they form oxides. And that should organize them in a way that says, they have similar characteristics. And this was the foundation for the modern periodic table. That same idea holds true for other chemical formulas. The example here, we have the chloride of calcium is CaCl2. What is the formula for the chloride of magnesium? There are two things that you need to realize. The first is you need to look at the periodic table and see where calcium is and where magnesium is. Are they in the same group? That's always the first question you should ask. So look at the periodic table and let me know. What do you see? Are they in the same group? Remember that a group is a vertical column. The symbol for magnesium is Mg, by the way. So are they in the same group? Let's double check that. So sometimes I'm like a little bit smart. So we used an example of magnesium or of calcium before. Magnesium is right above calcium. This is a group. It's a vertical column. Magnesium comes right above calcium. So yes, they are in the same group. No, we're talking about calcium and magnesium. So if the chloride of calcium has one calcium atom and two chlorine atoms, our guess would be that magnesium is the same thing. It would have one magnesium atom and two chlorine atoms. So the formula we would predict is MgCl2. The key here is knowing that the elements we're talking about have to be in the same group. Let's try another one. The formula for the oxide of sodium is Na2O. What is the formula for the oxide of potassium? You can put it in the chat. If sodium and potassium are in the same group, then they should look very similar for their oxide. We've got 2 atoms of sodium and 1 atom of oxygen. That's our sodium oxide. Potassium, it should be the same thing. Again, the key is knowing that sodium and potassium are in the same group. So you're going to have the same chemical formula. Questions about predicting chemical properties? Absolutely. Let me know when you're ready. I should have said no, I don't mind. Absolutely, I mind. I'm going to move on right away. Not at all what I meant. Okay. So here's the part that we've all been waiting for. Maybe you haven't, but I have. I've seen this coming down the road for a while. We're back at Electron Configurations, which for some students is a source of terror for Chem 103. Let me help you. It won't be that bad. This will be our review of Chapter 4. This is just a partial periodic table, but I'll still label it some and remind you of some of the things we talked about last week. First, I'm going to label all the different blocks. I will fight you, tablet. Okay. Sometimes you got to threaten the tablet. Everything that's outlined in black is the S block. You're filling the S orbital within that S sublevel. Each period, we know that terminology now, is a row that corresponds to a principal energy level. 1s, 2s, 3s, 4s. Next, we'll cover the P block. Putting that in purple. Hopefully the alliteration is not lost on you. It's purposeful. It's a lot of P's. Okay, I should stop. The P block, we're filling the P orbital. I should say orbitals, because there are 3. So that's filling up that P sublevel. 2p, 3p, 4p. The last thing that we have on here is a representation of the D block. We've only got 1 row of it, but we'll label it anyhow. We're filling the D orbitals here, which are part of the D sublevel. The one shown is the 3D. The S sublevel always has 1 orbital. Doesn't matter if it's 1s or 4s. There's only 1 orbital. The p sublevel has 3 orbitals. The d sublevel has 5 orbitals. So this is a review. There's another sublevel, the f sublevel. I don't even have it on this partial periodic table, but hopefully this is enough to kind of jog your memory. And if you understand this, then you'll be able to apply it to the f sublevel. Each sublevel holds a maximum of 2 electrons. So the S sublevel can hold a max of 2 electrons. The P sublevel can hold a maximum of 6 electrons. They don't have to be completely full. It can be partial. But they can hold up to 6 or up to 2. Now let's try writing the electron configuration for boron. Boron is right here. The principal energy level is N equals 2. And it has 5 electrons. How do I know it has 5 electrons? Good question, student who didn't ask. The reason we know is because for a neutral atom, emphasis on the neutral, the number of electrons is equal to the number of protons. So there's a large portion of chapter 4 reviewed, all on this slide. Let me know if you have questions before we move on to writing the electron configuration. If you're ready for it, let me know you're ready. Otherwise, ask your question. Then let's do it. Starting with, and I'll change colors here, the lowest energy level, the 1s. How many electrons can I put in the 1s? This is the 1s sublevel. Can you say that again? You cut out a little bit. The total number that we can put in there in one orbital is 2. So each orbital can hold 2 electrons. Since boron has 5 electrons, we're going to fill the 1s completely. 1, 2. We still have to add some more electrons to get to boron. So we go down to the next energy level, and that's N equals 2. How many electrons can we put in the 2s sublevel? Two. If we add up how many electrons we have so far, we've placed 4 electrons. So if we stopped here, this would be the configuration for beryllium, but that's not what we're interested in. We want to know about boron. So we have to go over to the P block, still in N equals 2, but now we're at 2p. How many electrons are we putting into the 2p sublevel? we're putting in 1. When you total up all of the numbers at the top, the superscripts, that should equal the number of electrons in your atom. Boron has 5, and that's how many electrons we've placed. That's the full configuration. Now I'm going to show you something a little bit different. We're going to do the noble gas configuration. I abbreviate noble gas NG. What this does is instead of writing all of the energy levels and sublevels that are full, we're just going to write a noble gas that has the configuration that shows all of the levels being full. So this comes in handy when you're writing a configuration for something really big. Boron, not so big, but we'll start here so that you get the concept. We're at boron, which is N equals 2. We need to look at the noble gas that is in N equals 1. So we look at the row 1, that's the period, and we're looking at group 8A. 8A is the noble gases. That's one of the common names that you'll need to know. Tell me, what is the symbol for the noble gas in the N equals 1 period? Yeah, I can repeat that. I want to know what the noble gas is that's in row 1. So it's row 1. We're looking at group 8A. What element is that? It's helium. The configuration for helium is 1s2. It's got its 1s sublevel completely full and it's happy. Now we need to write all of the electrons that come between helium and boron. That's everything in the N equals 2. 2s2 and 2p1. That's the noble gas configuration. We use the noble gas from N equals 1, that row, as the noble gas core. Then you fill in the electrons in the row that you're interested in until you get to your element. In this case, we filled them in up to boron. Let me know if I need to pause on this slide for a minute so that you can jot things down. We're going to do some more. Okay. So if it's, I don't get it, I have more examples and we'll walk through it again. So let's walk through another example. This time we're going to write configurations for aluminum. I'll label the table. We'll write out the full configuration first. Aluminum has 13 electrons because we're talking about a neutral atom of aluminum. If its atomic number is 13, that means it has 13 protons. That means it also has 13 electrons. We always start with the lowest energy sublevel. That's the 1s. How many electrons can the 1s hold? It can hold 2 electrons because it's got one orbital, and each orbital can hold 2 electrons. What is the next sublevel that we fill? We fill the 2s. So we just filled the 1s. I'm using my little dots to keep track of where we are. Now we are in 2s. It's the same thing as the 1s. We can fit 2 electrons. So far, we've placed a total of 4 electrons. We need a total of 13. Let's keep going. What's the next sublevel that we fill? We fill the 2p. This time we're putting 6 electrons here. The p sublevel has 3 orbitals, and you can hold 2 electrons per orbital. So that means 6 electrons total in the p sublevel. Now we've got 10 electrons. Where do we go next? We're now on period 3. And we fill that. What's next? We go on across to the p block. We only need 1 more electron to get to 13. So that's what we have. So if you didn't get the noble gas configuration, I'm not concerned about that yet. Do you understand how we write the full configuration? Because that's the foundation. So if you had question marks on the last slide, let me know if the full configuration is okay or if that's shaky. If that's shaky, then we may need to do some extra, okay? Well, that'll have to be outside of class. All right. Switch up the colors. We're going to do red now. This will be for our noble gas configuration. We're still going to do a configuration for aluminum, but it's not going to be as long. And here's the reason why. Aluminum is in the 3rd principal energy level. For the noble gas configuration, we're going to use the core of the noble gas that comes before aluminum. That means we're looking at N equals 2. What is the noble gas in row 2? It's neon. That is our noble gas. core. If we were to write out what the electron configuration is for neon, it would be, yeah, absolutely. Do you want to like pause, or do you want to put yourself on blast and do it out loud? Totally up to you. Okay. We're starting at the very beginning. Mm-hmm. Mm-hmm. Yes. And that is the configuration for neon. Notice that's what this is right here. 1s2, 2s2, 2p6. That's part of our configuration for aluminum. Instead of writing that, we're writing neon in brackets. Then the leftovers, everything that's in n equals 3, that's not covered by neon, we have to write out. So starting here, we say, okay, you go to the third row, that's 3s2. You go on over to the p block, 3p1. Mm-hmm. Yeah, so I'm showing you how the full configuration can be transformed to the noble gas. But you're not always going to be given the full configuration. You can write it out if you want to, if that's how you got to get there. But with practice, you can just go straight to the noble gas configuration. All right. I think I have one more example for us. I'm going to give you guys a couple of minutes to get started on the electron configuration for arsenic. The goal is to get to the noble gas electron configuration. If you need to write out the full configuration first and then go to the noble gas configuration, that's totally fine. If you can jump straight to it, go for the gold. I'll give you 2 minutes and then I'll check back in. I'll do it the full way just to make sure we're all on the same page. So if you want to put your noble gas configuration in the chat, you can. I'm not going to ask you to put the full configuration in because that's kind of a lot to type. So if you want to share your noble gas configuration, go for it. If you're just that gung-ho, you can share the full. But we're going to go and do it together too. This time we're looking at arsenic, aka rat poison. Okay. I'm not going to label these. I'm just going to write everything out, the sublevels. We always start at the very top of the periodic table. That's filling the 1s with 2 electrons. We then move on to the 2s and completely fill that. Then the 2p. Still not close to arsenic, so we're going to keep just filling everything up. Now we're in the 3s. Fill that up. Hop across the pond to the p block. We're in 3p land and fill that with 6 electrons. Now we're in the same row as arsenic, so we'll slow down a little bit. We know that we can fill the 4s with 2 electrons. Remember that what comes after the 4s in terms of energy levels is the 3d. And that is full. When it's full, you've got 10 electrons. Now we are in 4p, which is the block that arsenic lives on. We count the houses, 1, 2, 3. There we go. So that's a little bit long, but we got there. For the noble gas configuration, we're not going to write everything out. We know that arsenic is in N equals 4. We need the noble gas in N equals 3. You go to group 8A and find that noble gas. That is argon. You write that in brackets. Then we have to get from argon, this is our new starting point, all the way to arsenic. We start with the 4s2. Then we fill in the D block, 3d10. Then the P's, 1, 2, 3. Notice how argon took care of all that. So let me know how this was for you. Does it make a little more sense now than it did? If you still need help with this, that's okay. We're going to do a little bit more with configurations at the end of class. So we'll have more practice, but for time's sake, we need to keep moving. Just put a little note there and we'll come back to it. We'll talk a little bit about valence electrons. Then we'll take a very short break so you can shake your brain off a little bit, get some water, do what you got to do, and then we'll finish up. I'm going to highlight some of the things that you need to know for valence electrons. These are the electrons in the outermost principal energy level. They are the electrons that are involved in chemical reactions. When you're looking at a configuration, the valence electrons are in the S and the P. They're the S and P electrons beyond the noble gas core. So if we look again at what we had argon, 4s2, 3d10, 4p3. That's what we had for arsenic. The valence electrons are the S and P electrons in the principal energy level 4, because 4 is greater than 3. Even though 3d10 is higher in energy slightly, those electrons are not the outermost principal energy level. valence electrons, you're always looking at s and p electrons. To make it easier to figure out how many valence electrons you have, at least for the representative elements, those are the ones that have an A behind their group number. So group 1A through 8A. The group number indicates the number of valence electrons. So if I had fluorine, let's say, look at your periodic table and tell me what group is fluorine in. Tell me the number that comes before the A, because there's two different numbering systems for the groups. I don't care about the one that's 1 through 18. I care about the 1A through 8A. What is the group number for fluorine? Its symbol is an F. It's near the top. It's a non-metal, so it's towards the right of the periodic table. It's in group 7A. That means that it has 7 valence electrons. Why do we care about valence electrons? Again, they're the ones involved in chemistry. So we need to understand what's going on with those valence electrons. We can represent electrons, the valence electrons, using an electron dot formula, which is also called a Lewis dot structure. Same thing. It's a visual means of representing the valence electrons. You've got your core, which is the symbol of the element. That represents all the core electrons that we're not going to talk about. Then you've got the dots around the sides. Those represent the valence electrons. If you have 1 to 4 valence electrons, we'll have our symbol again. You just fill them in, 1 on each side, up to 4. If you've got 5 to 8 valence electrons, then you start doubling up. And the example I always use is if you have family come into town, you don't have any guest bedrooms or anything like that. That means you're sharing your bed. Happened to me, maybe it happened to you. You only share if you have to. You don't want to have your head next to somebody's feet unless it's absolutely necessary. Same thing with electrons. They only pair up if they have to. Let's do some examples, and that'll help to bring it all together. Is it okay if I move on to the next slide? Let's draw the electron dot formula for fluorine. We already did part of the work. It's a group 7A element, which means it has 7 valence electrons. To draw the Lewis dot structure, we're going to take the symbol for fluorine, which is an F, and we'll start filling in electrons around each side. We filled in all the sides. We've got 4 total, but fluorine has 7. So you go back around and fill in 1, 2, 3 for a total of 7 valence electrons. It doesn't matter which side has only 1 unpaired electron, as long as you've got 1 unpaired and 3 pairs. So those would all be correct Lewis structures. Let's do the second one. We've got aluminum. It's a group 3A element. How many valence electrons does aluminum have? It's got 3 valence electrons because of that group number. It tells you right in the number. 3A, 3 valence electrons. For our symbol, we just need 3 dots. One side should be open. Doesn't matter which side is open. But don't do something like that. That would be incorrect. Everybody clear on valence electrons, what they are, and how to draw electron dot formulas? Then let's take a quick break. We'll take a 5-minute break. We'll break until 3:43. So I'll see you back in 5. All right, everybody. It's 3:43. Time to pick it back up. We're almost done. We've got about 45 minutes left of class. We've got 2 topics left to cover. We just covered valence electrons, and we said they're the outermost electrons, the ones in the outermost principal energy level. We can relate that to ionization energy, which is our last periodic trend. So on that same periodic table, if you're drawing one during class, the one that has atomic radius and metallic character, add ionization energy. Ionization energy is just the amount of energy required to remove an electron in the gaseous state. In general, as you go from the bottom to the top of a group and from left to right across a period, ionization energy increases. Make sure that you add that. So that's the trend again when you're looking at the periodic table. Ionization energy increases. This is different from metallic character and atomic radius. If you can remember that ionization energy increases from the bottom to the top and left to right, the other trends are the opposite. And there you go. Now we're moving on to the last topic, which is ionic charges. we're going to be putting together valence electrons with electron configurations. Metals, which most of the periodic table consists of metals, react by losing their valence electrons to form positive ions. So we're going to take a minute to draw this out and really think about what this means. We've got the electron configuration, the full one, for a sodium atom and for a sodium ion. When we think about the atom, it's got a nucleus, and within that nucleus you have protons, which I'm putting in blue, you've also got neutrons. I'm putting those in green. We'll say that we have 11 neutrons. It's getting pretty crowded in there. Since we have a neutral atom and there are 11 protons, how many electrons should I have in my sodium atom? We've got 11 protons in a neutral atom. How many electrons do I have? I should have 11. Now we have this configuration here, and the smaller the energy level, so energy level 1, the closer it's going to be to the nucleus. Let's say this is my n equals 1. This is my n equals 2. And this is my n equals 3. N equals 1, I've got 2 electrons hanging out. N equals 2, I've got 8. Now this is not taking into account the shapes of the different orbitals and stuff. This is just a visual of how many electrons. In n equals 3, I've got 1. Sodium is a group 1A element. How many valence electrons does sodium have? I'll repeat that. Sodium is a group 1A element. The group number tells you how many valence electrons. Yeah, we've got 1 valence electron. That 1 valence electron is the one that's all the way out in the n equals 3. So that's what's boxed. When a metal reacts, it loses its valence electron. Now I'm going to recreate this same thing here and draw a bigger nucleus so I can fit all the particles. We've still got 11 protons in the nucleus. Nothing, that has not changed. We also still have 11 neutrons. We've still got that 1s2. We've still got 8 electrons in the Tues energy level. But we no longer have that n equals 3 electron. The 3s1 is gone. So how many electrons do we have in the sodium ion if we lose 1 electron? Seems like everybody ain't come back from break. We are done breaking. That was 10 minutes ago. Thank you. It's a class of 1. It's you and me. But that's all right. Thank you for helping me out. If we lose 1 electron, we started with 11. That means now we've got 10. Let's look at the charges. "11 protons" means that you've got plus 11. "11 electrons" means you've got minus 11. Your overall charge is 0, which is neutral. But then we lose 1. We didn't lose a proton because that would be a different element. We're not talking about that. But we did lose an electron. Now we've got more protons than we do electrons. And our charge is going to be positive. It's a positive 1. Let me know if you're vibing with this, if this makes sense. I go through the trouble of drawing it out so that you can see how you're losing an electron. Okay. Good. In general, the ionic charge from a metallic representative element, which means one of the ones that has an A behind it, is equal to the group number. Sodium was in group 1A. 1A elements lose 1 valence electron. to form a +1 ion. Doesn't matter which element it is from group 1A. So it could be lithium, it could be potassium. They all form the same charge when they form an ion. Now let's look at that in terms of the electron configuration. Now we'll look at magnesium. I'm labeling all the groups here for you. This is magnesium. It's in group 2A. What is the charge going to be for the magnesium ion? It's going to be 2+. The 2 in the group number tells us that the charge is equal to 2+, or +2, and that the magnesium atom has 2 valence electrons to lose. So when it forms that ion, that's what's going to happen. Let's write out the noble gas configuration for the magnesium atom. Magnesium is in N=3. We need the noble gas in N=2. That's going to be neon. Then we fill in everything between neon and magnesium to get us where we need to go, which means we start here. We're in the 3s, and magnesium fills both of those available slots in the s orbital. This is the electron configuration for the magnesium atom. That atom has 12 electrons. Neon has 10. We're adding another 2 in the 3s for a total of 12. Let me know if you're still with me. We haven't really done anything new yet. We just wrote the noble gas configuration for magnesium, the atom. Let me know you're still here. All right. Magnesium is a metal. It forms a positive ion. When it forms this ion, will it gain electrons or lose electrons? It's got to lose electrons. And I gave you the hint here too. That's all right. It's going to lose valence electrons because it forms a positive ion. A positive ion has more protons than electrons. The only way that that can happen is if you lose some electrons. We're going to lose those 2 valence electrons. The valence electrons are the ones in the outermost principal energy level. All of the s and p electrons beyond the noble gas core. That's the 3s2. Those electrons are going bye-bye. If we started with 12 electrons and we lose 2 valence electrons, how many electrons do we have left? We've got 10 electrons left. When we write the noble gas configuration for the magnesium 2+ ion, we're going to get rid of those valence electrons. And it leaves us with the noble gas core. If you look at the periodic table, neon has 10 electrons, just like the magnesium 2+ ion. We'll introduce the word isoelectronic here. That means it's the same number of electrons, and it's got the same electron configuration. Magnesium 2+ and neon are isoelectronic. So I'm going to let y'all drink that in for a second and then talk to me. I've got another example for us to walk through as well. So if you're like, I think I need another example, I've got one for you. If you have a specific question about this one, let me know. Otherwise, I think it would be good to just move on to doing another example. So let me know what your vote is. Example, we move on. Or if you have a question, you need to stay on this slide for a minute, say that too. Let's do the next example. Let's do the next example. We're going to go back to our friend aluminum again. What group is aluminum in? It's in 3A. That means its charge is going to be 3+. It will also have 3 valence electrons to lose. So right off bat, that's what we know just by looking at the group number. We did the electron configuration for aluminum a bit earlier, so I'm not going to tarry on that. That's an old-time word, tarry. You don't hear that. Nobody my age should be saying anything about tarrying nowhere. But I'm just an old soul. I apologize. So aluminum's got 13 electrons. I know that because a neutral atom has the same number of protons as it does electrons. Aluminum has 13 protons because the atomic number is 13. The full configuration for the aluminum atom, starting with the 1s, we fill that, 2s, 2p, 3s. Now we're in the home of aluminum in 3p, and we put 1 electron there. So we're not going to rehash that. If you need that, let me know, but we can't do it in class. That's a total of 13 electrons. Aluminum is a metal. Is it going to gain electrons or lose electrons to form an ion? It's going to lose electrons. How many electrons do we expect the aluminum ion to have? It should have 10 electrons. Based on that, what do you think the noble gas configuration is going to be for the aluminum 3+ ion? It's going to be neon. Just like magnesium, the aluminum 3+ ion and neon are isoelectronic. Means they have the same number of same number of electrons, and it's the same configuration. Due to time, we're going to have to press on because we still have to talk about negative ions. If you have questions about this, you can let me know right after class. I want to make sure we get to our announcements so I can remind you guys of some dates and some things. Negative ions. Non-metals form negative ions. So we're talking about nitrogen, oxygen, sulfur, all the things in kind of like that top right corner. Those are not metals, they're non-metals. And they gain electrons to form negative ions. Once again, I'll do an artist's rendition of an atom. Fluorine, it has 9 electrons. We know that because we can just total up 2 plus 2 plus 5 in our electron configuration. And for an atom, the number of electrons is equal to the number of protons. This means we've got 9 protons. We've got 9 neutrons. And now we've got to place these electrons. We've got 2 electrons in the 1s, and we've got 7 in the n equals 2 that are split up between the 2s and the 2p. Nonmetals gain electrons. Notice how we go from 2p5 to 2p6 for the fluorine ion. We've still got the same number of protons and neutrons. But our electrons are different. In n equals 1, we've still got the same 2 electrons. But we've gained 1 electron. That means we've got 8 in n equals 2. And again, this is not talking about the spacing and the orbitals. This is simply the number of electrons. If I gained an electron, I started with 9, I gained 1. How many do I have now in my ion? Yeah. How many electrons do I have in the fluorine ion? Yeah. Not a trick question. We started with 9. We gained 1. That means we now have 10. Let's look at our charge. For the atom, we've got 9 protons, 9 electrons. So the charge is 0. It's neutral. For the ion, we've still got the same number of protons. The protons never change when we're forming an ion. But this time we've got 10 electrons. That gives us a -1 charge. For negative ions, you always have more electrons than you do protons. The charge will always be negative when a nonmetal forms an ion. And I'll show you the rule for that on the next slide. when you want to determine, oh, it blacked out. Does everybody else see it? Because it still says that I'm sharing an application. Is it black for everybody? Oh, there it goes. Really, Blackboard? At the very end?